So we welcome today's speaker, Max Kaipel from the University of Cologne, who's going to talk to us about the many approaches to the tau cluster morphism category. So thank you, Max, for accepting the invitation, and you can start whenever you're ready.
Thank you very much for the introduction. Also for the opportunity to give a talk here. I will talk about the central object that has been the focus of my research so far, which is this tau cluster morphism category. And I hope that by the end of the talk, you will kind of understand what it is and what people are interested in it about, something like that, and kind of what we know about it and what I contributed to what we know about it somehow. So I'll start very elementary. If you have any questions at any point, please feel free to ask. And yeah, so just so we're all on the same page, let me fix some notation or some setting. So we have K, which will be a field, A, which will be a K algebra, which is finite dimensional. And we will study the category mod A of finite dimensional, right? That doesn't really matter today, A modules. Okay. So far, this is basically everything I need you to know already what that means. And now the first thing I will already introduce is this very important letter tau of the title, because I realized last week that in Catamarca that not everyone maybe knows what this tau means, and so that it's not a complete black box. Let me tell you what this is. So this is called the Ausländer Brighton translation. Let me just see if this other pen is a bit better. And what this Ausländer translation is the following. We need two duality functors. First, we have this with a T at the top, which is the A dual. And this goes from the category of right modules to the category of left A modules or modules of the opposite algebra. And we need the K dual, the K dual, which is this contrarian functor, which we assume goes from the category of left modules to the category of right modules. And now if I take some module M, I can look at what is called the minimal projective presentation. Minimal projective presentation. And by definition, this is, I take M, and I take a projective cover of M, with some map, which I will denote with almost the same letter, but this is a lowercase p. And then I look at the kernel of this map, 0, and I take a projective cover of this kernel. Okay, this is what I call a minimal projective presentation. And if I now apply this A dual functor, because this contravariant switches around the direction of the exact sequence, and here I now take a co-kernel of this map. I see my pen is dying again.
You have another pen if you want.
Thanks. And this is what I will denote by the transpose of M. Okay. And now the Ausländer translation, the last thing I'll write with this pen, is exactly dual, and then taking the transpose, which is defined like this. Okay. Look at an example. I'll not do the calculation in full, but oh my goodness, this pen is really good. Very nice.
Yeah.
Okay, so let's look at the following algebra. It will be the path algebra of some quiver with two vertices and two arrows. Modulo some ideal generated by the paths of length 2. This is actually also isomorphic to its opposite algebra. And here we can write what is called the AR quiver, which is somehow a picture of the module category that also shows you the Algebraic translations. So we have the projective one, which has some irreducible morphism to the simple one, which is the projective cover. This maps into the projective 2, which has a map to the simple 2, and the simple 2 maps into P1. And now the Algebraic translation is given on the symbols by this dashed line, by these dashed lines here. And you can also see that the projectives have no Algebraic translation, because if M is projective, then the projective covers itself. So the kernel is 0 and P1 is 0. And so here you have a 0 map and you get 0 as this. So the Algebraic translation of the projectives is 0. Okay. Now that we all know what this tau is, I can start talking about the area that I would say I work in, which is tau tilting theory. You can see the tau pops up again. And this is some generalization of classical tilting theory, which was introduced roughly 10 years ago by Adachi, Iyama, and Weiten. And while it's such a new theory, we will see later that there are already some results that date back a lot longer, 2014. And before we see those, the central objects we study in this theory are how rigid modules, defined as follows. So we say that some module A is how rigid if there are no non-zero homomorphisms from M to tau M. And very closely related, we say that the pair MP, where M is a module, any module, and P is a projective module, which I'll denote by this subcategory of projectives, is tau rigid. If firstly M is tau rigid, so M is tau rigid, and there is no non-zero homomorphism from P to F. Finally, one special case of these is that we say that MP is tau tilting if the number of non-isomorphic indecomposable direct summands, which I denote that is, number of pairwise non-isomorphic, stating the point, non-isomorphic indecomposable direct summands. Okay. M plus those of P is equal to those of A, where this somehow can also be seen as the number of isomorphism classes of symbols. Okay. So in this case, we would have that A, which I also call A, the rank, at this number, the rank of A will be 2. So in this example above, continued example, all indecomposable modules are tau rigid. Are rigid, which we see from the fact that the algebraic translation is 0, so clearly there are no non-zero maps, and S1 doesn't have a map to S2. Okay. And now, all the tau tilting pairs are following.
But this is a very particular case, right?
Right, and usually it's far from all indecomposable modules are tau rigid.
Yeah.
Usually that's far from the case. All the tau tilting pairs are the following. We kind of always have this pair, which is the sum of the projectives, because as I said, the algebraic translation of the projectives is 0, so this will always be tau rigid. And then in this case, we have some kind of symmetric structure where on one hand side we have the projective at 1 plus the symbol at 1, whose algebraic translation, which is additive, would be 0 plus S2. But since P1 and S1 both don't have any maps to S2, this means that it's tau rigid. Kind of symmetrically on the other side, we have P2 plus S2. And then we have S1. And now we've looked for some projective that doesn't map to S1, which in this case would be P2. Here we have S2 plus P1. And down at the bottom, we have something we also always get, which is the direct sum of all the projectives, but in the second part. So kind of like this, but on the other side, it's kind of easy to see where this is. Right? Just the projectives, 0, it's clearly satisfied. Okay. Any questions so far? I think so far, so good. This is a bit of an arm workout.
Yeah. I think it's because of the ink of that marker.
Yeah, maybe because it's bad. Yeah.
You can try this one as well.
All right. There's no. See if that's better. Yes.
And there are some heads.
Yeah. No, this one's really good for now.
So far.
For now. Right. Okay. So this is a very basic tilting theory. Now, one very important connection with tilting theory is with the following. Following kind of subcategories. So this definition goes back to Dixon in 1966. And it is that we call a full subcategory T of the module category a torsion class if it is closed under quotients and extensions. Okay. So if I take some module M, I can now look at kind of the quotient closure of this module, which I will denote by back of M. Some of this is all the factor modules N, which are those such that there exists some epimorphism from some number of copies of M to N. And this is not, in general, a torsion class because it may not be closed under extensions, but something that could be considered the first result of tau tilting theory due to Ausländer and Smale already from 1981, says that if M is tau rigid, then back M is a torsion class. This implies that this, or we can also show that there exists an injection from the set of tau tilting pairs of A into the set of word classes, given by simply sending torsion pair MP to back of N. And this now allows us to define something very essential for the tau cluster morphism category. This is some kind of reduction theorem, which says, which is due to Gustavo Hasso.
So wait, this is an injection.
Because different choices of M give different torsion classes if it's a tau tilting pair. Not in general for tau rigid, but for tau tilting. Yeah, so this is somehow one half of that injection between this and functorially finite ones, right? Which are exactly those of this problem. So Hasso in 2015, and in a slightly more general context, I will not write them all out, but Demone, Iyama, Reading, Brighton, and Thomas, in not much later, but it got published much later, in 23, showed the following. If MP is tau rigid, then the following subcategory M intersected with the left homoorthogonal with tau M intersected with P, the right homoorthogonal to P. So this, by definition, is a set of all N, all modulus N, such that hom N, tau M is 0. And somehow dually for this is all the N's, so that hom P, N is 0.
Could it be that empty? The fact M will be a purple. Okay, maybe I don't know where it's at.
Oh yeah. You're right. M per.
Yeah. Because
Yes.
M has no
class. Yes, you're right. Sorry. Yeah. It's had a. Yeah. So M per. Sorry. The other thing would just be fact N. So this subcategory of mod A is called functorially finite wide, but what this means, or what the important thing or interesting thing is that this is equivalent to mod B for some other finite-dimensional algebra B. And somehow these are the ones we're interested in. We're somehow interested in other module categories inside of mod A, and a lot of them are of this form. And the tau and somehow the tau rigid pairs are a way of finding these tau rigid, of finding these other module categories. This is somehow related to what I was also talking about in Catamarca. And I will just call this thing here J of MP for simplicity. Okay. Let's try the other one. So we want to kind of study these wide subcategories, right? Study these other module categories inside of mod A, and this is exactly what the tau cluster morphism category does. I will define that now, but I can already say in words that basically its objects are exactly these subcategories, and the morphisms are exactly such tau rigid pairs that kind of go between these, that help you find them. So this definition is due to a few people. Firstly, Iguza and Todorov showed or defined this category for hereditary algebras. in 2017. Then Huan and Marsh did it for algebras for which there are only finitely many Tautolling pairs, basic Tautolling pairs, in 21, and then Huan and Hansen did it for all finite-dimensional algebras. And what is the tau-cluster morphism category? The tau-cluster morphism category, which I will denote by a letter that I cannot write very well by hand at all. Category. It's supposed to be like some math frac W, something like this. Okay. I have to write this a few more times today. This tau-cluster morphism category has as its objects these what I call tau perpendicular categories. The tau perpendicular, somehow the perpendicular comes from all these orthogonal things, tau perpendicular, and then wide kind of is a property of these, which in a sense implies that it's a different module category. Wide subcategories J of MP for full MP of rigid. And the morphisms are somehow given now by how rigid pairs going between them are given by, I take one of these subcategories, I will now kind of just write it as W1, but just think this. Somewhat subcategory like this has mapped to somewhat subcategory W2, which is somehow defined by MP if MP is tau, but now what you have to be careful about is that this might have a different Alexander-Wrighton theory. So this is another module category. So it might have some slightly different Alexander-Wrighton translations. Everything that is tau rigid in A is also tau rigid here, but it may have more tau rigid objects. Objects which are not tau rigid in A may be tau rigid in there. And so now we take some tau W1 rigid, and such that if I take...
Sorry, how come?
What do you mean, how come?
Yeah, why? Why? I mean, the tau might not even belong to W1, right? The tau of A. It's an object in W1.
Yes.
Yeah.
Some object in W1 might not. It's a subcategory of A, of mod A.
Right.
So I said every object in W1 which was tau rigid in A is also tau rigid in W1.
Yeah. So I'm sorry. I'm a bit surprised by this because how they're do you have some kind of relationship between tau of W1 and tau of A?
Not that I know necessarily.
Because is tau of W1 a quotient of tau of W? So you know what I mean?
Yeah. So no, I guess the tau. Okay, maybe the tau is the same because it's a subcategory, but some of the tau rigids.
No, the tau is not.
No, the tau is not the same.
It's not the same. So yeah. So being tau rigid in A means no maps to tau to tau A.
Right.
And if this is 0, why this implies that there are no maps to the tau of W1? Because you are having two different objects, right?
Yes.
maybe there is. I mean,
I'm not sure. I'm not sure.
maybe I mean, for instance, I know that in certain subcategories, so the tau is not the same.
Yeah.
I mean, if you take a quotient B of A,
Yeah.
let's say,
Yeah.
then the tau of so in mod B as a proper quotient, in mod B the tau of you take some M in mod B, the tau B of M, I think actually was shown by Alexander and Smale in, if not that paper, in one close by, that tau B of M is a subobject of tau B of A, tau A of M.
Tau A of M, yeah.
And therefore, in that case, I believe, right, that being tau rigid in A implies tau rigid in B, because every map that goes to tau B would compose with this.
Yeah, in that case it's clear. But for this, I'm not sure what the relationship is. I've never really thought.
I mean, I mean,
but yeah, I think it, like,
if it is true, it's quite remarkable. But I mean, most probably it's true.
But if you take some tau rigid module, right?
Yeah.
You have this torsion-free functor, or you have this bijection between modules that are tau rigid, or at least compatible with it.
Yeah.
Which are, I guess, those that lie in the subcategory, or is that not true? Maybe not. You know, you have some bijection between modules which are compatible with this.
Yes.
And all tau rigids in the wide subcategory.
Yes.
The question is whether those are the only tau rigids, the tau rigids that are compatible with this are the only ones that also lie in the subcategory.
But being tau rigid in the bigger category and lying there would imply that to be compatible.
That would imply that. Yeah, because.
Because
then doesn't have morphism with tau M, and it has.
Yes. Yeah, it's in there, so it's compatible.
Okay,
so
if you're covered in A and you also lie in this intersection, then by definition you don't have a morphism to
you're compatible.
Yeah. And by definition you don't have morphism from P.
And you're in torsion-free class, so the F is the identity. And
exactly.
Then, that's very cool.
So then. Then you have a bijection between.
But it's far from being trivial, right?
True. I said we solved it now, but
it's pretty cool.
Yeah. All right.
Oh, that's good. And that's something very
right. Okay. So so.
Sorry for the interruption.
No problem. Yeah, it's good to clarify. So now we have this MP, which is tau W1 rigid, and we form this tau perpendicular subcategory. But now inside of W1 of MP, and this should be equal to W2. So somehow these tau rigid pairs are really ways of going between these wide subcategories, and these are exactly the morphisms. They're somehow, by definition, a map from one wide subcategory to another. By taking this thing.
Small comment then, so even if you have this injection of tau rigid pairs to torsion classes,
yes,
right? So now for these perpendicular categories, this is far from being an injection. So So this assignment for every tau rigid you
exactly. So you can take two different tau rigid pairs, but they might define the same wide subcategory. I guess I deleted the example already, but we can quickly do a spontaneous example, which we take the same algebra as before. Let me remind you, it was this. And with this Alexander quiver S2. It's not going to be this basically. E2, S2, E1, S1, S1. if I now take, okay, let's do just something very, very simple. If I take somehow the tau perpendicular category of P1, 0, this is all the modules which are orthogonal to P1, right? Tau of P is 0, and this P here is 0. So this is just P1 part. But this is the same as if I take this average pair, where M is 0, so the first two are 0, but now this P is P1, so I take P1 part. Right. And so these are two different average pairs, but they have the same subcategory associated to them. Okay, great. I'll erase this example now. But yeah, so this is our tau cluster morphism category. This is the category that we're kind of interested in. It captures all of the different, let's say, module categories that we can obtain from doing this tau tilting reduction, what it's called. Okay. Or maybe I just leave this here and then leave this here, and I can fit the properties on the left-hand side here. So I want to say some things we know about this category. At first, it may seem like if you first try to study this category, it feels a little bit difficult. It feels like this thing doesn't have any nice properties, but I think it does have some quite nice things to say about it. And the first one being that the classifying space, by which I mean the geometric realization of the simplicial nerve of the category, is a cube complex. What is a cube complex? It's kind of similar to a simplicial complex, simplicial set. A simplicial set is built from simplices, and a cube complex is built from cubes. So you can think that you take some cube and you glue to it some other cube at different dimension potentially. So put some square here, and then you, I don't know, glue another cube maybe like this. And then you glue a one-dimensional cube, something like this. This is kind of what a cube complex is, naively speaking. This is quite nice because these cube complexes are nice combinatorial and topological objects that we can say some things about. And moreover, the fundamental group, so this will be then some CW complex, the fundamental group of this classifying space, I write the classifying space as B of this category, is, I'll just say as quickly as I can, is somehow a vertex group of the groupoid, and kind of this way of writing Hipólito showed me last week, which is you take the set of all torsion classes of the form Fac M for M are rigid. This is a subset. This is a subset of the set of all torsion classes, and you can view such a subposet as a category with a unique morphism between any when you have an inclusion, right? And then you invert all the morphisms and make them make them isomorphic. So you invert all morphisms. This is some groupoid. You look at the vertex and you can kind of shrink it all to one object, right? How you make a grouped into a group in a sense. This is the fundamental group, and it's quite interesting to study in its own right. So this is sometimes called the picture group or the green group, and this thing would be the green groupoid. Why exactly it's called green? It doesn't have, it's not so relevant, but yeah. Anyway, because this thing is quite interesting by itself, the main question that people are interested in, let me phrase it like this. The main question I would say that people study about this category is this classifying space of this category a k-pi1 space? K-pi1 space. What this means is that the only non-trivial homotopy group, i.e. only non-trivial homotopy group, is in degree 1, and it's this thing here. This vertex group of what I will call G of A. It's non-trivial homotopy group is pi 1, which we know is isomorphic to this. And this actually allows us to then study, in a sense, this group by studying the space, or vice versa. Okay, let me raise this example now. And this is where this fact that we have a cube complex is very important or interesting, because from the fact that we have a cube complex, we can kind of translate some topological criterion for this, which is somehow due to Gromov from a year I don't remember now, sometime in the 80s, and kind of translate it to our setting, which was done by Iguza in 2014, which says that some of this classifying space is a k-pi1 space if the two following sufficient conditions are satisfied. Firstly, there exists a faithful functor from the morphism category to this groupoid that we've just defined. And secondly, something that I will not talk about so much, it's called the pairwise compatibility property. Is satisfied. Whatever that means, it's not so important. The second thing holds if the rank of A is less than 3, if A is, so this was done by Barnard, Hansen, 23, I think, is parametric of finite, or I'll say most Kane types by Iguza and Todorov in a data paper, or, for example, if A is Nakayama-like, which somehow means that the underlying quiver is either a line with any orientation or a circle with any orientation, but yeah, but so that it's got finally many types of pairs. And this was done by Hansen and Iguza. Okay, so this is the second property. And this first one is kind of the one that I have mainly been studying. When does such a functor exist? Okay. Any questions so far?
Doesn't seem to be the case.
Sorry?
It doesn't seem to be the case. There are no questions.
No questions, yeah. That doesn't seem to be the case. Okay, then, let me just have a quick look at the time. Okay, so let me now kind of say two things about this category, which is that, okay, this is quite nice, but one challenge that has kind of existed since the beginning of this time cluster morphism category is that the associativity of composition of morphisms is very difficult. Morphisms is very difficult to prove. Okay? And somehow this problem, or this fact, has inspired different approaches. So far we've only seen the algebraic approach. But this challenge, that it's really very difficult to show that associativity in this category is satisfied, and so that this is actually a category, is very difficult. And this spawned two different approaches that I will try to tell you about very briefly. The first one is based on the following observation. If we take tau rigid pair, then this defines, through this minimal projective presentation that we saw, a complex. So P is this projective, and P1 is P1 to P0 is that minimal projective presentation of M. This is somehow a complex in the bounded homotopy category of projective A modules, okay, with some nice properties. And now, the first approach to solving this problem was done by Berber in 21, who defines this tau cluster morphism category by a thick, which just means triangulated, full subcategories of the bounded derived category of mod A, generated by such, like this, two-term complexes. Okay, so if you kind of take this, you look at the triangulated subcategory that it generates in here, you can kind of see this as your objects in the tau cluster morphism category, and then this kind of leads now to a simplified proof of associativity. Simplified proof of associativity. And this leads to a generalization of this tau cluster morphism category to DG algebras, maybe with some adjectives before, like positive or non-positive proper DG algebras, and some DG categories with some adjectives. This is the one approach, and for the second approach, I have to give one definition, which is of a G vector. So the G vector of a module M is following. It's the difference vector-wise between two vectors that come from the minimal projective presentation. This is somehow a vector in our algebra, where we can now write this minimal projective presentation of M as somehow a direct sum decompositions of the projectives, and we count how many times these projectives arise in the minimal projective presentation. Okay, so from rank A, 1 to rank A. Okay. Now we can define the G vector cone of some pair as the non-negative span, so non-negative combinations of the G vectors of the indecomposable direct summits. So of GM1, which is the first indecomposable direct summit of M, all the way to GMR, and then minus the indecomposable direct summits of P, the G vectors of these. P1 to GP S. Okay. And with this, we can do the second approach. We can now just quickly define the following geometric object, which has, which is just a collection of all of these. So we call this C of MP, this non-negative linear span. And now we just kind of look at all of these cones for all the tau rigid pairs. And the second approach now, due to Roll, Tata, Pfeffinger, and Williams, 23, is to define this tau cluster morphism category via equivalence classes of these G-vector cones. This is what I call these things, G-vector cones, where we kind of just say that C, MP is in an equivalence class with C, M prime, P prime, whenever this subcategory of MP is the same as this subcategory of M prime, P prime. Right? So with this, you can kind of convince yourself that you probably get the same subcategory. That's the same category. This also leads to a simplified proof of associativity. This is what they did, and what I did is to show that this leads to a generalization to arbitrary simplicial fans, which is somehow simplicial fans, which are just like this, collections of cones, so non-negative linear combinations in Rn, which behave nicely, so they intersect at faces, and every face is also a cone of this collection of cones. Okay, but the importance of this is the main theorem of this work, is that this implies, or really I should say that if this object, this collection of cones, which I call the G-fan, if this is a hyperplane arrangement, then there exists a faithful functor from the tau cluster morphism category to the picture, which is, as you remember, one of the two sufficient conditions for it to be a K+1 space. And I've not done an example in a while, so I'm sorry about that. Let me go back to the example we had previously. The G-vector fan of this looks as follows. I just write the individual G-vectors. So the G-vectors of the projectives, because they are their own projective cover, are the standard basis vectors of Rn. G1, G of P1, G of P2. Here you have the negatives, and here you have G of S2, and here you have G of S1. So in here you have the cone of the pair P1 plus P2, P1 plus S1, comma 0. Here you have the pair P1 plus P2, comma 0, and you can fill out this picture accordingly. Maybe I should say that here where you have the negative G vector, this then would be the cone of S2, P1, which if you remember was one of the tensorial pairs. And you can, I drew it earlier, you can kind of see that shape I drew it in, even though I didn't draw the arrows, kind of see that shape that I drew earlier as in such a way. Let me make a remark that we know, beside this family of algebras, for which this is a hyperplane arrangement, we know it for two other families, which I'll write. We know the same, or we know the existence of a faithful functor for only two other families. Okay. It's hereditary of finite or chain type. Finite or chain type, this time all chain types, by Iguza and Todorov, or when A is a K-stone algebra. What does that mean? Basically, it means that if I take some interval like this in the this will be an interval of the poset of torsion classes. And if I write a Hasse diagram, which somehow has an arrow whenever I have a cover relation, it's a K-stone algebra if the shape of this interval is one of the following. It's either a square, a pentagon, or a hexagon. So for these two algebras, the class of algebras, we know it, and for algebras which are hyperplane arrangements, we know it. Okay, I could finish here, or I could talk 10 more minutes. 10 more minutes? All right. And so this was the first, so this result was the first main contribution I made to this calculus morphism category. And the other thing I then asked myself was that, kind of similar to something Hipólito asked earlier, so it's quite a natural question to ask yourself, if you have a quotient algebra of A, what is the relationship between A and the quotient algebra? So I take some ideal of the algebra, and now I can form the quotient algebra, right? And this has the property that the category of A quotient I modules is a subcategory of those of A. It's a very natural question, I think, to ask, what is the relationship? This should be now section quotients. What is the relationship between the tau-customorphism category of A and tau-customorphism category of A quotient I? The problem of this with the approaches we have seen so far is that in general, if I take, and this is exactly what Hipólito said somehow, or very similar, is that if I take the tau-rigid modules of A, and then I intersect this with the module category that is that of the quotient, in general, this only gives a proper subset of the tau-rigid AI modules. This kind of makes it difficult to simply say, okay, I just quotient everything, because suddenly you're killing all of these tau-rigid modules and you're no longer getting non-zero things, like you're sending a lot of stuff to zero. And this is where the following observation comes in. which is that in contrast to this relationship where we have proper inclusion, if I take the torsion classes of A and I intersect them with AI, this is actually all of the torsion classes of AI. And this observation inspired the following final one or two main results, which is that kind of similar to Berber, we did a derived category approach, and Scholl-Tafler-Treffinger, we did a geometric approach. Now I take a poset theoretic approach, studying kind of the poset partially ordered set properties of this set of torsion classes. I say that we can define the tau cluster morphism category via equivalence classes of intervals of the form back m or tau m intersect p part, which I say is equivalent to fac m per m prime. This is such a tongue twister. M prime per tau m prime intersect with p prime. Okay, so these are intervals of the poset of torsion classes, and I identify this whenever I have, again, that these subcategories, these perpendicular subcategories, coincide. So again, we can believe that it gives you the same subcategory. But the crucial thing is not that this is maybe such an insightful new definition, but kind of because of this observation, it has quite powerful implications. So as a corollary, or basically what follows from defining it like this, with a bit of extra study, is that there exists a functor from, let's call it F, from tau cluster morphism category of A to the tau cluster morphism category of the quotient. And if the set of torsion classes, which is just a poset, is finite, then I'll just mention two for things that follow from this. Then this functor is firstly surjective on objects, and maybe the most important corollary is that there exists a faithful functor from the tau cluster morphism category of the quotient to the tau cluster morphism category of A. And with this, we can extend every faithful functor we have from A to faithful functors from the quotient. So now we also know it for quotients of all of these three classes of functions. And that's where I'll finish. Thank you very much.
Thank you very much. Are there any questions?
More than questions, I would like to make a comment. I mean, I think this last result, the fact that you can show now, I mean, the existence of faithful functor from the tau cluster morphism category of A induces a faithful functor from the tau cluster morphism category of the quotient is probably the strongest result that there is in this.
Thank you very much.
No, in this line of research. To be honest, this is, yeah, I mean, at least was the motivating question that I always had. Somehow. In general, there is, I mean, there are some ideas how to prove it for every infinite algebra.
Ideas, yes.
Right, I mean, one would be every algebra is a quotient of some hereditary algebra in some sense, but is far from being tame. So,
Right.
but and also hyperplane arrangements you might want to generalize. I mean,
Yeah. So somehow, it's sadly not. I've obviously thought about this. It's obviously not. It's or not obviously at all, but it's sadly not true that every algebra is a quotient of a hyperplane arrangement. Or at least I should really say that I need here that this is actually a finite hyperplane arrangement.
yeah,
This is the problem.
Yeah.
Finiteness. I think otherwise, maybe it is true. I don't know, but sadly, it's not. It's not true that it's a finite. That it's a quotient of a finite hyperplane arrangement. And one example is already just take some Nakayama algebra on 4 vertices with any. It doesn't matter what relations you choose here. The problem is if you make this a hyperplane arrangement, what you have to do is you have to add reverse arrows on every thing, and suddenly this becomes a Brouwer graph algebra, which comes from a 4 cycle, and there's some result that says that this will be infinite, so it will not be finite. Yeah, and I guess similarly, for hereditary algebras, you have a
Is there a way to translate this into some to the combinatorial side once again?
which result or
I mean, this idea of the quotient, right? I mean, this quotient algebra, you can see the one-chamber structure as a subsimplicial. I don't know if it is a subsimplicial fan, but
it's somehow you just kind of merge cones and remove cones, right? Like if I take a quotient of this algebra, for example, I could, if I remove the arrow, if you remember this came from this, AB, if I now remove the arrow B, then it's the same as removing this, right? So the question is, what is the relationship between these two? And there is definitely some relation, like quotient fan. I think such a thing exists. And maybe one could have done it with a similar approach, but this is much more difficult to do geometrically, I think.
right.
That's kind of that's my kind of argument, is that to study this relationship between A and A quotient I, all the other approaches, it's either not possible or really difficult and tedious.
Yeah.
And with this approach, with defining it as intervals, it makes it relatively easy.
Right.
Or doable.
Yeah.
But much more natural, I think, rather
Yeah.
than some geometric or algebraic arguments. Well, I think really algebraic, very difficult, or maybe not possible. Geometrically maybe possible, but maybe more difficult than this.
Yeah. Maybe, So I'm coming to the positives.
Yes.
So did you do it for, I mean, the torsion class, so the lattice of torsion classes in mod A over I is a quotient lattice of those.
Yes, that's the key point. Yeah.
So can you translate this for every nice quotient of lattices?
Yeah, so I thought about whether there's nothing stopping you from defining a calculus morphism category basically for any semi-distributive lattice.
Yes.
Because that's one of the things I show as well, is that if two algebras as a whole set have the same lattice of torsion classes, they define the same or equivalent calculus morphism categories.
Right.
The problem with doing it and the way you do this is that basically you can encode the structure, you can kind of recognize these intervals only poset theoretically as some join or meet intervals, whatever that means, and you can encode these white subcategories somehow as collections of join irreducible elements which label these intervals. The problem with doing this for an arbitrary semi-distributive lattice is that basically it becomes so restrictive, like basically there are no nice examples of where this makes any sense.
Outside of
finite-dimensional algebras.
Right.
The key point for algebras is that, or what makes it very nice to define them, is that if I take some interval, which these are determined by the bottom arrow, and then some arrows that come in, I now form the join of these elements here, which is the least upper bound, or least upper, bound. When I do this, this uniquely, so the values, you can give some values here, B1, B2, B3. The values of these three uniquely determine the rest of the interval.
Yeah.
But if you have an arbitrary semi-distributive lattice, you can have kind of the same structure down here, but you can have that this interval is not actually the same as this interval, even though the labels on these three things down there coincide.
I see.
Which, for an algebra, this kind of is enough. So then really you have to say that, okay, there are equivalences of equivalence classes of intervals where really the whole thing coincides. And then it's, you kind of really shrink down the number of examples where you get something almost non-trivial, you know, a lot of the time you just get some, or I don't know, maybe not non-trivial, but it's like there's not really any motivation to do it for all semi-distributive lattices, but it's definitely doable.
Right. I see it.
And the question for those would be, if you use for arbitrary simplicial thing, do you still get these other nice properties like that it's a cube complex and that, what is the fundamental group of this thing, you know? This I don't know. But defining this category by equivalence classes, you can do.
Okay.
But what the point is, I don't know. That's why I didn't really do it.
No, of course.
Yeah.
Are there any more questions?
Do you have any idea of the restrictions imposed on the category by this fact that the Schoen's representation is a cubical set, cubical complex?
Well, this is not an assumption I make somehow. This is a property of this definition. And somehow where this comes from is, in a sense, the ways you have to complete how rigid pairs into how tilting pairs. So somehow you can see the cubes in this in a sense as kind of what I drew here already. So you start here and you want to complete this into a pair. You have one cube like this. You have another cube like this. And so you kind of glue these cubes together, and this is a one-dimensional cube as well. So kind of this is where it comes from. If I now do this generalization, I say I did this for arbitrary simplicial fans. The word simplicial implies that it will be a cube complex again. That means that the vectors that span a cone are linearly independent. If you have not linearly independent things spanning a cone, you can probably do the same thing, but then you will no longer have this cube complex property. I hope that somehow answers your question a bit, or gives some idea of what this cube complex property kind of means.
Are there any more questions? I do have a question.
Yes.
Do you have an example or a family of examples of algebras such that such a category as its classified space as not a K/1 space?
Yeah, excellent question. No, we don't know. So somehow one could say it's a conjecture that this is always a K/1 space. We know examples, and I should have maybe mentioned this, but good that you asked. We know examples of algebras which do not satisfy this pairwise compatibility property. So remember, there are two sufficient conditions. I think it's a very valid conjecture to assume that the spectral functor basically always exists. We know that the pairwise compatibility is not always satisfied, which doesn't imply it's not a K/1. It just implies that we cannot use this way to show it's a K.
Right.
So it would be very interesting, but I don't really have the skills to try and find an example where we know this pairwise compatibility doesn't hold and show it's a K/1, or find an example which is not a K/1. Any of these would be very interesting and exciting to me. So yeah, the problem is that, as I said, the pairwise compatibility is satisfied if the rank of the algebra is 3 or less. So you need to go to rank 4 at least, and then things are big and complicated. So it's a bit painful to do this.
Right.
But this compatibility it's satisfied for algebraic generations?
Not necessarily.
Not necessarily.
Not necessarily.
Okay. Yes.
Any more questions? Well, thank you. It was very nice.
Thank you very much.